Hello. In the last lecture, we looked at large displacement analysis of a cantilever beam with a load at the free end of the beam. One end is fixed, other end there is a concentrated load F, and we used elliptic integrals based solution, which is completely analytical, where we were able to convert the differential equation in the transverse displacement W in terms of only one variable called P, which was related to the slope at the free end or the loaded tip and was able to solve using elliptic integral solution. Today we will extend that concept and in fact make it even more profound by using what is known as elastic similarity principle. So, let us look at this elastic similarity principle, which enables us to solve many other problems than a cantilever with a load at the tip. So, this elastic similarity in the large displacement analysis of beams is quite interesting, and this is a slightly difficult topic. So, we should pay attention to whatever we are doing. So, let us recall some of the important equations that we had begun with in the last lecture, and these are indicated here. So, if you look at the first one, it's going to indicate this theta L and theta. Theta L is the slope here, that is theta L, where we have arc length. So, we go in terms of this parameter S, which is measured along the deformed beam. When that S is equal to L, that theta L, any other point, if I take let us say an intermediate point, let me use a different color. If I use an intermediate point over there, now the slope at that point, if I were to write, that will be just theta. So, what this equation, the equation here shows is that when I integrate from 0 to theta L, then the whole thing is equal to L, where theta is the variable here, which when you go from here theta is equal to 0 because the slope is 0 there, and then increases up to theta L. When I do this limits from 0 to theta L, this particular integral, which involves the force F and Young's modulus E, moment of area, second moment of area I, then I will get back my length L. On the right hand side we have 0 to L ds. All this came from ds by d theta, which is curvature, and we came from that equation. We also did a change of variables from theta to phi. So, here we have the same equation. So, this is the same equation that now is in terms of phi rather than theta. Our limits also have changed as per the change of variables equations that we had used. Okay. This was done in the last lecture. We also did in the last lecture the following, that when we have this, if I indicate this as the w axis and x axis as shown over there, that w L by L, x L by L, that is w L by L will be from the original beam to the deformed one, that is w sub L, and x L is from there to here. Note that we are indicating the coordinate system in the deformed profile of the beam and not in the undeformed one. So, this is the deformed profile of the beam, that is a characteristic of geometric nonlinear problem or large displacement problem. So, here we indicated this in non-dimensional form W L by L equal to something which depends on this non-dimensional factor eta, which is square root of F L square by E I, where you know all the quantities. F is the force, L is the length of the beam. Before and after we assume that the length is the same, Young's modulus E, second moment of area I, and then there is this P that needs to be solved. If we go back to the previous slide, that P is over there, that depends on this value eta. So, if I know eta, I can calculate P and vice versa. So, we have that P depends on eta. The whole thing is a function of eta, which is a nonlinear function, because these are capital F is the elliptic integral of the first kind, complete because it is pi by 2, incomplete phi naught or that value at p, and then we have second elliptic integral E complete and then incomplete. It is a nonlinear function of eta, and xl by L also can be derived like this. We had written this, but we had not done this part, but if you follow the derivation there where we had the horizontal span of the distance between the point that you have taken the fixed one to where it is deformed, that will come out to be this. That was not in the last lecture, that in the further reading if you see you will get that thing. It is not at all difficult if you follow the last lecture. So, we have done this. Now, let us look at this limits of this integral. So, it was from 0 to theta L over there, that gave us this L on the right hand side, and on the left hand side we rearranged it a little bit, that also comes in terms of this 0 to L ds, where this limit is sine inverse 1 over p square root of 2 to pi by 2 for phi. Theta anyway is a slope that varies from 0 to theta L at the loaded tip, whereas the phi has this strange thing that somehow starts at some value which is sine inverse of 1 over p square root, goes up to pi by 2. Pi by 2 is some notion of completeness is there, it goes to 90 degrees, but what is this? Why is it starting from here, and what happens if we go less than this? So, we have, let us say if I do the phi axis here, let us say that pi by 2 is some kind of an end for this, because theta L is the end of the beam. So, let us say that pi by 2 for the phi is the end. We are starting somewhere here which is sine inverse 1 over p square root of 2. What if I go to the other side, go all the way to 0, that is phi equal to 0. At this point phi is equal to 0. What does that mean? Okay. Let us look at that. So, I substitute phi equal to 0, then the first equation, that is this one, let us go back, that is this one here, gives us sine, I would say theta 0, let me say, that is it corresponds to where phi is equal to 0. I should be clear when I say that, I mean at phi equal to 0, that will give me 2 p square sine square phi, but sine phi is 0, that will become 0 minus 1. So, what I get at that point is when phi is equal to 0, theta corresponding to phi equal to 0 will be, because sine of that is minus 1, that is minus pi by 2. So, what is happening is that if I have the beam like this, and this is what we had said, this angle at this point theta equal to 0, at this point theta equal to theta L, but now we need to go to a point where this theta correspond to phi equal to 0, where it is minus pi by 2. That means that this one with respect to horizontal, that is what we are measuring, right. So, here if I were to, I will just use a different color, this theta L that we are talking about, we are measuring with respect to horizontal. So, with that it should become minus pi by 2. So, that we get if I were to extend this curve until this becomes something like this, where this is pi by 2, since we are measuring from here to here, from where it is to vertical horizontal line. So, this is actually minus pi by 2, we are going in the other, see here we are measuring from horizontal in the clockwise direction as theta. Here when it goes counterclockwise, it gives the minus sign. So, we have to go like this. So, in order to have this geometric interpretation from theta to phi, we take the clue that when phi is equal to 0, theta is minus pi by 2. So, with that we will be able to guess what this geometric interpretation of phi is. So, let us look at this principle of elastic similarity. Now, keeping in mind what this phi geometrically means. This is all taken from the excellent book by Frischfee called Flexible Bars, written in 1962, and there is a picture of that taken from that. The notation used in that is different from the one that I am using. So, we should not get confused. We should see what symbols stand in his book and in this presentation. So, we have this one now. What if I extend it beyond B? That is what we said, to take that phi back to 0 value. If I do that, then I can interpret this as a point A which has a vertical column A C double prime. Okay. So, originally BC prime deformed to BC. Now, we say that the vertical column A C double prime, when we apply a load, it would buckle to a shape that is ABC. If I fix at A, then I can actually afford to remove the support at B. I will still be able to hold the shape of the complete bent profile of the vertical A C double prime column or strut. Okay. A C double prime, when you apply a load F over there, it would bend like this. I should not show F here because the F is not acting in that configuration, F is acting actually in the deformed configuration. So, again if I were to remove the support B, it will stay the way it is. So, what is phi now? We have just shown going back all the way from B to A with this interpretation. Now, it turns out that if I extend it and imagine that there is a point A and there is AC double prime vertical strut, then I can join this line, horizontal line from A, and then let this point go all the way to Q. Then I get this circular arc or quadrant of a circle APQ. Okay. So, here is where our phi B is. So, we have to take this B, extend it vertically up to P and then join to O. Remember, this is a quarter of a circle, and that is how this phi is defined, and that phi is measured in this manner. So, from horizontal line AO and then OP, that inclination is phi B. Again notice how we got P, we went from B up until it meets a quarter of a circle and then come down. So, the phi that we measure is actually this angle that we have shown there, and this is the elastic similarity. The way the cantilever beam from B to C prime would deform to BC would be same as a vertical column AC double prime would buckle to ABC, and when we fix at A, we do not need the support at B, and this is the elastic similarity between a cantilever beam and the buckling of a vertical column or a strut, as Frischfee calls. Now, we have this H here, that is the horizontal span or radius of the quarter of a circle. Okay. We need to find that. Before we do that, let us understand this arc length interpretation in this elastic similarity. Now, I am going from theta 0 to theta, or phi from let us say the corresponding thing here would have been not 0, but it would have been our arc length whatever that sine inverse 1 over p square root of 2. But what we have done now is I am varying this phi from 0 to phi. If I do, it will go to 0 to some s phi. Likewise, theta I can go from let us say a point B or some other thing corresponding to this. It should not be 0 0, they do not correspond, some other limit over there. When I go to theta, I would get s theta, that is from 0 to s theta, and the 0 again. So, in fact, correspond to 0, this as we already said, it is minus pi by 2. When I go to minus pi by 2 theta, that will be 0 to s theta ds if we do s theta. What does it mean? When I take a point, let us say somewhere over here, then from here to here there is an arc length S phi. Okay. If I take this point over there, again how do I compute the phi? I have to extend vertical line there and join that to this. This would be my general phi. Okay, that phi that I show here, this should be calculated. I have to draw a vertical line and join this. With respect to horizontal, I get phi. When I do this integral from 0 to phi, what I get will be that S phi, that is this arc length from here to here. That is interpretation here. When I go from here to B, I will get this arc length that is in the dashed line. When I come from B to C, then I have to subtract whatever arc length I have from here to C, that is ABC minus AB. If I do, then I will get the original length of the cantilever beam that I had as L. So, this interpretation elastic similarity, you can imagine a number of situations using this diagram, or this especially the interpretation of this phi, that is the key concept here. Now, let us also look at, by knowing that, what are the coordinates of the deflected profile at any point B beyond any point D beyond B. So, if I take a point D, again I have to take this interpretation. In fact, this is not the point I should take. So, we should actually imagine this will be, let us call this point E or something. This is of no significance. If I take a point here, I draw a vertical line and join this, that becomes my phi D. Okay. So, actually let us not say that is not D. So, we can call instead of D E, that will be the phi D. Okay. So, again we have to go up here and join that, that becomes my phi D. So, if I have that, the coordinates here, if I take the W x thing, W by L, that is this little distance, that is very little, okay, how much ever that has deformed, that will be W, and the horizontal coordinate in this x, that will be x here, that W by L is given by that and x by L is given by this in terms of whatever angle that we have. In general, phi D I have called, so that can be phi D, and then from phi B we are measuring, and this also will be phi D, any point. Okay. So, you also know the coordinates, this arc length interpretation, whatever point, you can take a point here, here, let us say I take a point here, I drop a vertical line and join that to this, that becomes my general phi. So, I can take that over there and over there, then I would get the W at that point from here to there and x from here to there in this coordinate system of W and x. Okay. That is how this interpretation is graphically, and equations are as what they are shown on this slide. Okay. Now, what about this h? We have not talked about that yet. So, what is the radius of this quarter of a circle that we have? What is that h? That h can be interpreted by knowing that x by L, that from the previous slide where we discussed, it is 2 p by eta. Again, eta is a non-dimensional number, that is square root of f L square by E I times cosine phi b minus cosine phi. Okay. If you, that is a general one. So, now what happens when we go all the way to the end, that is at point O, where phi actually becomes 90 degrees. So, that is 90 degrees. Okay. Then if I go all the way, then that cosine phi, that will be 0. So, I get xl, that is x is general for any phi. If I take that all the way to the end, which is phi equal to pi by 2, that is from B all the way to C, and I do, this becomes 0. So, I get xl by L is 2 p by eta cosine phi b, implies that cosine phi b is equal to square root of eta times x sub L by 2 p L. What is x sub L? X sub L is from here to here, that is my x sub L. Okay. Now, we can also see that cosine phi b is equal to xl by h. This is xl and h is this radius here. Cosine phi b is also equal to xl by h. By comparing these two, we can get that h. So, cosine phi b is xl by h from here, which is also equal to square root of eta xl by 2 p l, and by from here we can get h to be equal to 2 p l by eta or 2 p, because eta is f l square by E I. Substitute, it will become L gets cancelled, square root of f by E I. So, this square root of f by E I, Frischfe calls it k. If we are referring to the book, this will come handy. So, h is 2 p by k in his notation. We are sticking to what we have, symbols that we have used. I am not introducing additional symbol k in this presentation. Okay. That is why we can get h also. Now, if you look at non-dimensional portrayal again, so W L by L, X L by L we had for complete one here. So, we have that phi going all the way to pi by 2, starting from phi naught, which is what we had in the previous lecture. In this lecture, that phi naught we are denoting as phi b, because the 0 corresponds to, in this presentation, where phi becomes 0, which is actually in theta equal to minus pi by 2, or this phi becomes 0. Okay. So, this for going complete L, both horizontal here and then transverse W L. Now, with the arc length interpretation, any other point I take, I will get, if I go from phi 1 to phi 2, then W 2 minus W 1 by L is what I get. I can go from phi 1 to phi 2, both elliptic the first kind capital F, second kind E. Likewise, horizontal x 2 minus x 1 by L 2 p by the square root of f by E I, cosine phi 2 minus cosine phi 1. So, we are able to get any length. So, that is, if I have this one going all the way something like this, if I take any 2 points, let us say that let me draw that circle with the same blue color we had used. Let us say I have something like this, that is a quarter of the circle. If I take any 2 points, then I have to, let me change color again for clarity, I have to do vertical line and join this, vertical line, join this, then I get these angles. Let us call this phi 1 and this is phi 2. Then what I get, if I say W 2 minus W 1, what I get is from the horizontal that we had. Okay. So, whatever distance that is there between this and this, that will be W 2 minus W 1, and likewise the horizontal distance from here to here, that would be x 2 minus x 1. Okay, by taking 2 points, one over here, another over there. So, this is a point 1, point 2, we can get that in a non-dimensional form. So, we can actually solve a number of problems, starting from a strut that was vertical like this and original horizontal that we had, and anything in between. So, this means that if there were to be an inclined load, okay. So, how does that come about? Inclined load, so far we have taken a load that is transverse to the beam, but now if I take a point such as what is indicated over there and draw a line tangent to this profile that we have, general profile that we have, this green one still has force. It goes from, let us say, T to C triple prime, that would deflect to TBC profile under the action of this load F. Again, I do not show force F here because that has not deformed. When that force acts at C triple prime, that will change it from TC double prime to TBC. And again, we do not have to put the support at B when we do that, just like we had argued about this vertical strut AC triple prime. If we fix this, then I do not need that. So, in the inclined load, I can again take this general phi angle draw a vertical line to TR and then join R to O, I get this. Then I can remove the supported B. Okay. This is what again Frischweg gives in his book, as if we have turned the coordinate system. You see this coordinate system, what you had like that has been turned over there based on the angle. Okay. That angle is whatever angle that this makes with this, we can call it alpha. Okay, that is what he also shows an alpha angle here. Again, other symbols are different in the book compared to the symbols that we have used in this presentation, but what it means is that you just have to rotate the coordinate system and do the translation, because we are, our measurement is from here, because this is where our x is and our w is. Now it has moved over here and has been rotated. So you have to do a coordinate transformation by doing this some translation from here to here, and also a rotation, because now it has changed, the coordinate system is changed. So with respect to that, if there is inclined load, because the load were to be here, it is inclined, right, compared to the original one which were to be transverse like this and inclined. So the inclined load, if you do, you have to do this coordinate transformation based on this. All that information is right here in this diagram. Okay. Now, how do we use this elastic similarity principle when there is a moment load? Now, in this originally when there is force F, it would have deformed like this. Now, there is an additional moment M, then how do we do this? It will not be the way it is shown here, because this is for when the force F is acting. Now, when there is moment acting, everything here, that is all this portion will change. How does it change? So, what Frischweg recommends is that imagine now that there is a rigid lever. So, this is a rigid lever attached at point C horizontally, and now at a distance, the length of the rigid lever is E, which is taken as m divided by F. We want to bring in the effect of moment at the point C. So, what he recommends is, let us move this force F from point C to another point over there, which is a distance E from here. Now, if you see the way we have defined E, if I multiply this F with this E, then I get moment here, which will be m, because E is defined as m over F. When I multiply this E with F, I get m, and I get back the force F here. So, I am getting moment and force over here effectively. So, I get the moment m, I get the force F. If you imagine that there is an extension of the beam, which let us say deforms to something like this. So, this C to whatever point this is, let us call this D prime, that would deform to CD, and the whole thing also changes. Now, the previous one that we had, that AHP, all that, this quarter of a circle will change now, because there is F and M, or rather we have F at a farther point beyond C. So, we have to change that circle, exactly same construction, only thing is it will become larger, as we will see here. Now, I am putting that point, this O has changed, correspond to D, I took it right above the D. The D CD is the extension of this CF, which may be longer where the force is being applied, okay, to get this thing, all right. So, now we have a new thing, and I need to get that new H here. In order to get this new H, we already know the E. The E, again if you go back to this, E equal to m by F, and now we can get that E in terms of the geometry here, that E by H, that E is from here to here, which is same as that. H is the new H that we need to find, radius of the circle, that is equal to cosine phi c, which we also know to be equal to this E by 2p square root of F by EI, that comes from the way the cosine phi c is defined here. So, from here we can relate this H to E. When H is there, H is again related to P here. So, we know everything in this diagram. Okay. Again it takes a little bit of interpretation. I put the original figure from Frischweg's book. If we look at the geometry right, we get this relationship, then we know the E is a function of H is a function of P, only unknown is P now. This P is not the same as that what we had when there were to be only a vertical force at point C. Now the force is acting at this end of the rigid lever or extension of this to create the effect of movement here. So, to recalculate that P. How do we get that P? In order to calculate that P, what we need to know is this length A to B is LAB, B to C is LBC, C to D is LCD. What we are given is only this LAB, LBC. LBC equal to L is all we know, but we can write that with our arc length interpretation. This LBC or L equal to LBC is the integral that goes from phi B to phi C. We already know phi C from the previous thing. Cosine phi C is equal to this, we already have. Okay. H was P by square root of F by E I that we had derived. So, phi C is known to us and phi B is anyway known to us because that was sine inverse 1 over 2 square root of P. So, these two limits are known. So, I can get this LBC by doing that elliptic of the first kind that we had from the arc length interpretation that has the unknown which is P. So, P will be the unknown in this equation. So, since I know L, I can calculate P. Once I know P, I can get everything here. That is, when we change that force over here, our radius H had changed. H depends on P, that P is obtained from this equation. So, you can solve using this principal elastic similarity a case with moment load as well. It can get even more complicated. What if there are two transverse loads? So, there is a P1 and P2. Here I have taken the figure from Frisch's book directly, and again his symbols are different. He uses psi where we have used theta, and let us not get confused, and of course he uses P for force, we are using F for force and so forth, but the concept is clear. When there are two transverse loads like this, we know that in the linear case we use principle of superposition. Whatever we get with P1 displacement, we add that to the displacement we get when there is for P2. So, that cannot be done with nonlinear, but this elastic similarity principle lets you do almost that. It is not linear superposition, it is some kind of a non-linear superposition using this graphical construction and the corresponding equations. So, if you do that here, this is a diagram from Frisch's book where we have this picture where the original one is shown with H equal to 2P by K. Again I said uses a K which is square root of F over EI. Okay, that is a new symbol we have not introduced, but he uses, and he says that from A to B, okay, there is a P1 and then after that there is a P2 over here at point C. So, if you want to know what is AB deformed, he says introduce a new force P, that is over here, you see that P over there. He says that introduce P such that this P is equal to P1 plus P2, because at point B you would feel the effect of P2 as well as P1, right, when we do the shear force diagram, and also you would feel a moment which is this P2 times whatever this distance B is, that distance B. So, it defines this B as BR by G, where G is P2 by P1 and BR is this distance. It is a lot of geometric construction corresponding to that, each of that there is an equation that we can see, but what he is saying is that if you want to know the profile from A to B, you should have the total force P1 plus P2 put at a distance which is at BR, such that the moment here that is felt is P2 times the distance from here to here which is B. Okay, that is how he puts that. So, he gets that, and corresponding value of P which is over here, you have one equation. The end point, unlike the previous one, it is not equal to pi by 2, that phi b here is not equal to pi by 2, which was the case earlier. So, that phi b is an unknown, this is an unknown here, okay. And of course, the p is also is an unknown, p is also an unknown. We have two unknowns here, and then we have this other one b to c, which he says is simply another one of this, where it is at B, imagine like a cantilever beam from going to that to C, which is straightforward, which we have discussed earlier, that gives you BC. So, AB is controlled by one P, and then BC is controlled by another one, which is P2. This P2 is an unknown. Our unknowns now are 3, P2, this P, the original P is there, and then phi B. What equation do we have? Again uses geometry, that this length BR can be obtained in two different ways, because we know various distances here. That is, if I look at this distance B, that comes from the cosine one, and BR comes from the cosine for the first case. If I take this triangle from here to there, here to okay, this BR goes from here to there to here, I will get BR. Other one goes from here to there to here, I get that B. B and BR are related the way he defined. So, he gets that additional equation. So, we get previously from the length equation, here we get for P one equation, and phi B comes from the cosine equation. Now, the third equation is this relating this B and BR. He gets 3 equation, 3 unknowns, and solves it. It is a lot of geometric construction, but the corresponding equations, it worth studying carefully to see that it actually works out in a way that when there are 2 transverse loads, you have 3 equations in 3 unknowns. Unknowns are phi B, P, and P2. That P corresponding to this, there is a P2 corresponding to this. You are superposing them. These are non-linear things, yet you are able to superpose in order to get the combined profile. In fact, he argues that if there are n loads, let us say I have a beam where there are n loads, any number, okay, there is let us say P, F1, F2, F3 and Fn. If you have that, then you would do these diagrams, each one of them, and the unknowns will be 2n minus 1 here, and so many equations we have to get. When n equal to 0, which was the first case we had done the last lecture, we had only one unknown, which was that P that we had, or that P was related to the slope at the end, theta L. Okay. When n equal to 2, which we briefly discussed now, unknowns are 2 times 2, 4 minus 1, 3 unknowns, which were 2 P's. There was a P and then another P2 for the second arc that we considered, and then there was this phi B at that point where it is. So, when you have more loads, you will have more and more unknowns, but what is interesting is the differential equation originally was converted to equation 1 variable. If there are 2 loads, then it becomes 3 unknowns, eventually it becomes 2n minus 1 unknowns. It is a very efficient way compared to finite element analysis. It may be difficult to believe, but we have fewer, instead of solving differential equation, here we solved only elliptic integral equation with only one unknown P. In the case of 2 loads, you will have let us say 2 differential equations, load 1, load 2. You are not supposed to add them up linearly, right, you have to have a non-linear one. So, it becomes a difficult one to do, but now we are able to do it in fewer variables and able to get the solution. All that I have discussed today is from this book called Flexible Bars. Those of you who are interested should study this book in the chapter 2 in that, which explains all of this and a lot more. What we need to understand now is that using this principle of elastic similarity, we can solve a cantilever beam with the tip load in any direction. Inclined load is possible and moment load is possible, multiple loads are also possible. So, anything can be done using this principle of elastic similarity. It was a work done in 1960s, somehow it seems to be forgotten, but there is a big need to get it back if you want to do large display analysis of flexible bars. What we will see in the next lecture is a set of examples to understand whatever we have discussed in the first lecture and this lecture, that is in this week first lecture and second lecture. Third lecture of this week we will do some numerical examples to understand this. Later on we will see how this insight can be taken further to be useful for compliant mechanism analysis as well as design. Thank you.